Hey everyone, welcome to The Explainer. Today, we are diving right into the hidden and frankly sometimes chaotic complexity of taking machine learning models out of a pristine research lab and dropping them into the messy, unpredictable real world. It is a journey full of unexpected twists, but don't worry, we've got a blueprint to help guide us through it. Okay, let's get right into this. For a long time, the machine learning community really struggled to establish a standard process. Because, building a model in a perfectly controlled notebook, that's one thing. But deploying it to make actual high-stakes business decisions without a structured framework, that almost always leads to ad hoc chaos, results you can't reproduce, and ultimately totally failed projects. We absolutely need a way to bring order to that chaos. So, enter the hero of our story, CRISP-MLQ. Yeah, I know, it's a bit of a mouthful, but it stands for the Cross-Industry Standard Process for the Development of Machine Learning Applications with Quality Assurance. Essentially, this is a battle-tested, systematic methodology designed specifically to cure that whole ad hoc development style. It injects rigorous quality assurance into literally every single step, ensuring that what you build actually works, scales, and delivers real value. Here's the quick roadmap for the explainer today. We're going to hit the 6 critical phases of this framework, starting with the ML blueprint, then business goals and data prep, engineering the model itself, rigorous evaluation, the actual deployment, and finally, the ongoing monitoring and iteration. All right, phase 1, the machine learning blueprint. So, machine learning development is fundamentally different from traditional software engineering, right? It's much closer to a giant, exploratory scientific experiment. We've got 6 phases here, and what's absolutely vital to grasp is that this workflow is not some rigid, one-way waterfall. It is highly interconnected and incredibly iterative. Early-stage planning directly dictates your late-stage success. If you find a problem in phase 4, you don't just shove it through to phase 5, no way. You loop back to phase 2, or maybe even phase 1. The results from the later phases literally force us to constantly re-examine the early steps. Moving along to phase 2, business goals and data prep. To make this super concrete, let's use a running example. Imagine we are building a computer vision model for a massive food manufacturing plant. Its job? To detect bad, burnt, or broken cookies on a conveyor belt before they end up in a customer's box. So, phase 1 is business and data understanding. Before we write a single line of Python, we have to make sure this project is actually feasible. We do that by defining clear, measurable key performance indicators, or KPIs. For our cookie factory, a KPI is not just, oh, we want high AI accuracy. It needs to be a business metric. Think time saved on manual cookie sorting or a 20% reduction in customer complaints. Those KPIs become the ultimate measuring stick for the whole shebang. Once that goal is locked in, we hit phase 2, data engineering, and right away we run into a massive make-or-break hurdle. Think about our conveyor belt. Let's say 98% of the cookies are perfectly golden brown and only 2% are actually defective. This is what we call an unbalanced class. If we train our model on that raw data, the AI is just going to be lazy. It'll guess good cookie every single time, brag about being 98% accurate, and completely fail to do its actual job. To fix it, we have to use data engineering strategies, like oversampling the bad cookies or undersampling the good ones, just to level the playing field. Listen, data engineering is incredibly rigorous work. We're talking data selection, cleaning, feature engineering, standardization, all of it. But honestly, the absolute most crucial task here is unit testing for data. By vigorously cleaning the data and setting up automated tests right now, we stop massive errors from propagating down the line. If dirty data slips through here, it literally poisons the entire pipeline downstream. Okay, phase 3, actually engineering the ML model. This is the really fun part, where our carefully curated cookie data is finally fed into the algorithms. But here's the crucial point. This shows that powerful ripple effect between the phases I mentioned earlier. Back in phase 1, our business context revealed a catch. The factory doesn't have reliable internet. The model has to run locally on an embedded camera right over the belt. Because of that early discovery, well, now in phase 3, we have a hard technical constraint. The model must have extremely low latency and demand almost no resources. We can't just spin up some massive, cloud-heavy algorithm. We are forced to engineer a specialized, highly compressed model so it actually works on the factory floor. Another massive piece of model engineering is documentation. Like we talked about at the start, a huge complaint in ML is that you just can't reproduce the results. To make sure our cookie detector success isn't just some random lucky fluke, we have to meticulously track the metadata. We're talking the exact algorithm, the specific training datasets, the hyperparameters, the runtime environment. This guarantees that if things go sideways later, we can perfectly recreate the model from scratch. Next up, Phase 4, rigorous ML model evaluation. So, we built the model, but before it ever sees a real physical cookie, we have to validate it offline. We throw the kitchen sink at it, noisy data, blurry images, weird factory lighting, you name it. Now, I want you to think about this for a second. What actually happens if our model completely fails the test and totally misses those time-saving KPIs we set up back in Phase 1? Does the whole project just die? Absolutely not. Remember, machine learning is exploratory by nature. Failing an evaluation test isn't a dead end at all. It's a feature. It simply triggers our iterative feedback loop. It tells us, hey, send the workflow back in time. We might loop back to Phase 2 to collect way more images of burnt cookies, or tweak the data pipeline. Heck, we might even loop all the way back to Phase 1 to sit down with the business stakeholders and redefine what success actually looks like. Which brings us to Phase 5, deployment and going live. This is graduation day. The model finally leaves the lab and gets integrated into the real-world factory software. But look, you don't just flip a giant switch and cross your fingers. You use highly specific rollout strategies. Maybe A/B testing, where you evaluate the AI side by side with human sorters. Or a canary deployment, rolling it out to just one single conveyor belt to see how it handles a tiny bit of traffic. Or blue-green, if you need to switch instantly. And crucially, safe deployment means you absolutely must have a concrete fallback plan. Because if the AI suddenly starts throwing perfectly good cookies into the trash, we need an immediate way to revert to the old system so we don't shut the whole factory down. And finally, Phase 6, monitoring, maintenance, and iteration. Now, what's really interesting about this phase is that it literally never ends. Let's talk about model stillness. Your model might be an absolute rock star on day 1, but the real world shifts. Imagine the factory introduces a brand new recipe, say a double chocolate chip cookie that is just naturally much darker in color. Our model has never seen this real-world data before. Suddenly, the AI thinks all these brand new, perfectly good cookies are horribly burnt, and its accuracy just plummets. That right there, that is model stillness in action. So how do we fight it? We use the continued model evaluation pattern. We are basically continuously watching the live data stream for what we call drift, like that new darker cookie recipe. When the system detects that the incoming data has drifted and performance is taking a hit, it directly triggers the pipeline to update. We grab those new images, label them, and automatically fire them back through the lifecycle to retrain the model on fresh data.
Which leaves us with this really relentless question to ponder. Sure, your model works today, but is it going to survive tomorrow's data? The machine learning lifecycle is never just a one-and-done project. It is a continuous, living, breathing blueprint. By really embracing this iterative nature of CRISP-MLQ, you make sure your AI doesn't just survive out there in the real world, but actually adapts and thrives over time. So keep exploring, keep iterating, and hey, thanks so much for joining me on this explainer today.